Carboxylic acids can react with alcohols in order to form esters through a condensation reaction. We call it as esterification. However, this reaction happens very slowly in the absence of an acid. So when we introduce an acid catalyst and follow this esterification reaction, we call it a Fischer esterification. In today's lab, we will be following a Fischer esterification reaction in order to produce this ester isopentyl acetate, which is also called banana oil. To make that, we'll be reacting acetic acid with isopentyl alcohol, and acetic acid is going to be the carboxylic acid, and isopentyl alcohol will serve as the alcohol. And we are following this reaction in the presence of concentrated sulfuric acid, and we'll be producing isopentyl acetate and water as a side product. Often in esterification reactions, we see the elimination of a small molecule like water due to the condensation that is happening between the functional groups of the two reagents. So in Fischer esterification, it will be the OH group from the carboxylic acid molecule condensing with the hydrogen from the OH in the alcohol in order to generate water. As you can see, this reaction happens forward as well as back towards forming the reagent. So the forward reaction is where the reagent molecules combine to give the products. The reverse reaction is where the products combine back to break down into the reagents. These kind of reactions we call reversible reactions, and when the rate of the forward reaction is the same as the rate of the reverse reaction, we say that this reaction has achieved equilibrium. That is, when you look at it from the outside, it appears like there is no net change in the concentrations of these products or the reagents, because the reagents are combining to form the products at the same rate the products are breaking down into the reagents. These kind of reactions, which can achieve equilibrium, can be explained through an equilibrium constant Keq, which is equal to the product of the concentrations of the product molecules over the product of the concentrations of the reactant molecules. So whatever amount of reagents that we add in the beginning, this reaction is going to stop or achieve equilibrium at some point, and after that the concentration of the product will not change. But in order to obtain a high yield of isopentyl acetate, we need to manipulate the system in order to favor the forward reaction, so we will be able to get a lot of isopentyl acetate. We can do two things to achieve this. One is we can remove the water as it forms. So you can see if we take away the water, then the product of isopentyl acetate concentration to water concentration, this total value is going to reduce. So I'm sure you all heard of the Le Chatelier principle. For a reaction, at equilibrium, if we introduce a change to one of the reactants or the products, the reaction will either move towards the forward direction or the reverse direction in order to get rid of that change we introduced. So the change we introduced here is removing the water, which causes the product between these two to become low. So to keep the equilibrium constant, the product of these two should go down as well. That means the forward reaction is favored. The other thing we can do is we can add a lot of one of the reagents. That makes the product of these two larger. That means to keep the equilibrium constant the same, the top part of the equation should also increase its value. So in other words, again, we are favoring the forward reaction. So these are the two steps that we can do in order to make sure that we get a high yield of isopentyl acetate. In this slide, we're going to look at the reaction mechanism for the Fischer esterification between acetic acid and isopentyl alcohol. So what happens is the sulfuric acid will help activate this oxygen on the carbonyl group of acetic acid by protonating it. So now this oxygen is lacking electrons, so it's going to pull the electrons that it was sharing with the carbonyl carbon, which makes the carbonyl carbon more electrophilic and more susceptible to undergo a nucleophilic attack from the oxygen coming from the alcohol. So we have a condensed molecule over here, and next we see a proton transfer. So there is a OHR group now attached to this carbonyl carbon, and there will be a proton transfer where this proton is transferred to the oxygen that was in the OH of the carboxylic group. And after that proton transfer, now there is this OH2 plus group, which is going to leave as a water molecule, and this bisulfate ion is going to come back and accept this proton, which will allow this oxygen to form a double bond again. So you can see the sulfuric acid does not get used up in the reaction because it's a catalyst. It donated a proton and later accepted a proton, so it did not get used up. Whatever it gave in the beginning, it gained it back in the end. And we end up with the ester product. Not all alcohols can participate in Fischer esterification. Especially tertiary alcohols do not participate in Fischer esterification reactions because there are too many substituents on the carbon next to the oxygen, which kind of crowds the oxygen atom or causes steric hindrance around it that limits its ability to approach the carbonyl carbon of the carboxylic molecule in order to follow the nucleophilic attack. So you'll have to remember that Fischer esterification is not feasible for tertiary alcohols even when it's mixed with sulfuric acid. However, we want to still remember this tertiary alcohol can react with sulfuric acid and undergo a dehydration reaction in order to produce the respective alkene molecule. So if I gave you guys a question asking, I mixed a tertiary alcohol with a carboxylic acid in the presence of sulfuric acid, will this undergo Fischer esterification? The answer will be no, it won't, because of the reasons I explained in the previous slide. However, it will still react with sulfuric acid, undergo a dehydration, and produce the respective alkene. Now we have the experiment set up for the experiment today in forming isopentyl acetate. We have isopentyl alcohol, acetic acid, sulfuric acid all combined in a 5 ml vial with a spin wane, and we fix it to a condenser in order to allow a refluxing for a long period of time for 45 minutes. Remember, we do the refluxing in order to make sure the reactant volume does not go down during the long reaction incubation time. And we have a drying tube here with 2 cotton plugs having some calcium chloride in between, and the purpose of this is to absorb any moisture. Once the reflux is complete, we will have this product mixture, which should contain isopentyl acetate and also have leftover acetic acid because we used an excess amount of it. So that should be in this mixture, and the yellow color comes from the ester molecule. First of all, we are going to wash the solution, which is actually an organic solution, right? So that's going to be the organic layer. We're going to wash it with water at least twice in order to draw out water that is combined with the organic layer. And next, we are going to wash the organic layer at least 3 times with sodium bicarbonate, which is a base, and the sole purpose of washing the organic layer with sodium bicarbonate is to remove that excess amount of acetic acid. So acetic acid will react with sodium bicarbonate to produce sodium acetate, carbon dioxide gas, and water. Carbon dioxide will leave the system as gas. Water will be soluble in the aqueous layer, and sodium acetate is a charged molecule, so it's an ionic molecule, and ionic molecules also solubilize in the aqueous layer. So this way we can remove the excess amount of acetic acid that was left in the organic layer. Once we've done that, then we are going to do a couple of drying steps. Drying as in removing any traces of water from the organic layer. So the first drying step we're going to do is wash the organic layer with saturated sodium chloride. This is basically a very concentrated table salt solution. So highly concentrated salt solutions are very good at absorbing water. Therefore, when we mix it with the organic layer, any water droplets that were trapped in the organic layer should move to the salt water. After that, we are going to do a final drying step by adding anhydrous sodium sulfate, which should absorb any more leftover water. And after that, we are going to pass this organic solution through a filter tip pipette and collect it into a 3 ml pre-weighed 3 ml vial. The reason we pass it through the pipette is to get rid of any sodium sulfate particles that could be mixed with this, and we are going to get the actual weight of the ester product by directly measuring the weight of this vial. And that's why we didn't want any sodium sulfate passed on to this new vial. Finally, we are going to obtain some gas chromatograms. You did gas chromatography in OChem 1, and we do this to look at the purity of our ester sample. Like I mentioned earlier, we made sure to remove any leftover acetic acid by mixing it with sodium bicarbonate. So we know there are no more acetic acid left in the ester sample. But there could be maybe a little bit of isopentyl alcohol that is left over if it did not completely react. So there is no straightforward method to easily remove it during extraction. Therefore, we are going to see if there is any significant amount of isopentyl alcohol present in the final product mixture. Here we have the GC spectrum just for isopentyl acetate but isopentyl alcohol by itself. And we can see that it has a peak around between 1.25 to 1.5 minutes. Then we get a GC for the product isopentyl acetate, and we can see that same peak appearing between 1.25 to 1.5 minutes. So this little peak here is isopentyl alcohol, and the big peak represents isopentyl acetate. Remember, we used to calculate the proportion of each of these molecules present in the sample based on the area under the peak, right? Actually, you don't have to do any calculations here. Just by eyeballing, we can observe that there is very little amount of isopentyl alcohol present in the final ester mixture. So we can state that this sample is almost 99% pure and it's mostly isopentyl acetate. You can include this description in your conclusion explaining the purity of the ester sample. Finally, we're going to quickly look at the calculation of theoretical yield. It's going to be very easy for this lab because the molar ratio between the reactants as well as the reactants and products are all 1 to 1 to 1 to 1. So we know the amounts of each of the reagents we added, 28 millimoles versus 7.3 millimoles. Since it's a 1 to 1 ratio, obviously isopentyl alcohol will be the limiting reagent. And since the molar ratio between that versus the product is also 1 to 1, we can expect 7.3 millimoles of isopentyl acetate to form theoretically. Then, in order to get the theoretical yield, we multiply the number of theoretical moles times the molecular weight of isopentyl acetate. You might wonder then, why did we add so much acetic acid? That was to make sure the forward reaction was favored as much as possible, forcing almost all of the 7.3 millimoles of isopentyl alcohol to be converted into the acetate. So that's all for this lab. Like always, feel free to contact me if you have any questions while you're working on the lab reports. Thank you.